Hello everyone and welcome to the second season of our webinar series. While you watch the webinar, our technical support specialist Dima will be scanning this screw nut, which is approximately 27 millimeters in diameter, and we will share our results with you at the end of the webinar. We stay on the air, so those of you who have not had a chance to see the micro in action and actually can see how easy it is. And now I would like to pass a microphone to our technical support specialist, Vadim Zaremba. Hi, Vadim.
Hello. Okay, so let's get started, I guess. I hope everyone's here. Thank you for attending our micro webinar. So today we will be going over some key aspects of the Artec Micro 3D scanner, and we'll provide you with a general overview of its capabilities. Now, this should help you gain a better technical understanding of the device. So here on this slide, we see an outline of the material that we have prepared for today. First, we'll take a brief look at the scanner specifications. Then we'll go over the two key features that make the Artec Micro scanner stand out from the competition. That's the automatic scanning path and the glare noise reduction feature. We'll also briefly cover the usefulness of manual scanning paths. Then we'll move on to the micro scanner's parts and accessories description, where we'll be explaining, among other things, how to place the object at the proper height inside the scanner. An explanation about the high-resolution scanning mode then follows. Then we'll have some examples showing the possibility of mounting the object on the scanner platform, as well as geometrical aids that can be placed around the object in order to assist with the registration. And then finally, we'll illustrate a scanning and post-processing workflow, just explaining different possible scanning techniques, showing some example data sets of objects that we scanned, and that kind of things. All right, so let's get started. While the specifications of the scanner can actually be found on our website, we still want to take a brief moment to go over them with you. Now, the Micro is a blue light, structured light 3D scanner. What it does is it projects a fringe pattern onto the surface of an object and reads the distortion of that pattern via two 6.4 megapixel cameras. The maximum size of an object that you can scan with the Micro is 90 by 60 by 60 millimeters. While the object can theoretically be somewhat larger, this will require some manual repositioning and will not be as convenient as if you're working within the specified size limit. The maximum weight load somewhat depends on where the center of weight is, but officially we recommend not to exceed 3 to 3.4 kilograms. That's 6.6 to 7.5 pounds on the micro scanning platform. Like all other Artec scanners, the Micro can scan in full color, and it can generate textures of up to 24 bits per pixel. Now I would like to briefly address the way we are positioning the Micro in the 3D scanning market. So as you may know, the Micro is our first fully automated desktop 3D scanner. It's mainly intended for applications that require a considerably higher level of accuracy and resolution than would be possible with the Space Spider, and where the object is relatively small, up to 9 centimeters in height, as we saw earlier. Now, the Micro in itself is already a high accuracy, high resolution 3D scanner. But in addition, and this is key, Artec Studio 15 maximizes the main advantages of the Micro, making it clearly stand out from other similar scanning devices. Notably, the Micro is now capable of fully automated one-click 3D scanning. This means that all you need to do is click a single button, and the software automatically chooses the best scanning path and optimal viewpoints for making a perfect scan, without any additional input being required from the operator. And this automation, that's that unique capability which helps the Micro truly stand out from its competition. The automatic scanning path feature is right here, as you see in the picture on the right. And here we have a short demonstration and comparison of automatic versus manual scanning. So this leopard ring was scanned using the automatic scanning path, as well as the manual small complex scanning path and the manual large complex scanning path. Here on this slide, for comparison, we have the automatic scanning path video at the top and the small complex path video at the bottom. The automatic path ended up capturing 70 frames simply because the object is so complex and full of small holes. But this actually brought great results. The manual small complex scanning path captured its pre-programmed 49 frames from the fixed viewpoints that you can see on the right. And the result was actually less satisfactory. Some areas were not scanned properly, while others were fused with noise due to too many similar angles being captured. The manual large complex scanning path, while it's not pictured here, it did capture its pre-programmed 56 frames. And while the result was marginally better than what the small complex path option delivered, the automatic path still won overall, both in terms of coverage as well as noise. It's important to understand that in this particular case with the leopard ring, the automatic scanning path chose to capture more frames than did the manual path. And that's simply because the object was so complex. In other cases, if the object is very simple, the automatic path will oftentimes capture less frames than will the manual scanning path due to its smart analysis of the object. Now, if you're wondering how the automatic scanning path works, here's a diagram that should help. Basically explained, the software analyzes the scan after each 10 frames, and based on the data, decides which additional 10 angles to cover. Then it reassesses the data again, and continues doing this until the object has been completely scanned. This feature is unique to Artec Studio 15, and will help you beat a lot of the competition. And finally, if the automatic scanning path mode alone isn't enough of a killer feature all by itself, we have something else on top of that. A glare noise reduction algorithm, which is also exclusive to Artec Studio 15. This fully and automatically locates any frames with excessive surface noise, such as these right here, and eliminates them during the meshing process that we call fusion. This automatically results in much cleaner meshes without any need for manual noise removal. Now, in case you were wondering where these noisy frames come from to begin with, look at the pictures on the right. They may occur due to the surface properties of the object combined with the scanning angle. So for example, if the object is somewhat reflective or has a perfectly flat area and the scanning light hits it at 90 degrees, that's when a noisy frame will be created. Any competitive device based on the same technology, and most of them are, will have these noisy frames as well. But from what we have seen in competitive software packages, the noise is a nuisance and needs to be removed manually, not with Artec Studio. In order to see an example of the glare noise reduction algorithm in action, let's zoom in and take a look at the raw data of this Octopus ring. On the left, you have a clean frame. On the top left, sorry, you have a clean frame, yeah. And then on the bottom left, you have a frame with clearly visible noise. And I marked that with a red rectangle. Now, after performing the fusion with the glare noise reduction algorithm enabled, we get a very clean result that you can see on the right. Now, this image is also ideal to show you that the glare noise reduction algorithm is smart. So the bump that you see on the fusion, and I marked that in yellow, that is not noise. It's actually something that is present in the original geometry of the ring. And here you can see that bump in the photo, which was taken under a microscope. So while the noise that was sticking out of the scan surface was effectively removed by the algorithm, the small bump on the ring's surface remained untouched and was reconstructed correctly. And finally, here is the result of the ring scan. Please remember that the automatic scanning path, as well as the glare noise reduction algorithm, are the two killer features that make the Artec Micro stand out from the competition. And as you know, we are constantly improving Artec Studio, and it's quickly becoming a powerful piece of software which none of our competitors can match. Now, with Artec Studio's yearly releases, and with at least one midterm update, the Micro will be a good investment for many years to come. New features will be regularly added to improve the user experience. Now let's spend another short moment talking about the manual scanning paths. It is possible to use a number of preset paths as well as create custom paths. This can be very useful if the same type of object is being scanned over and over again, for example, for quality control or inspection purposes. Here is one preset path in particular that can be very useful, the rotation only scanning path. This can be used if the object is ring-shaped or if it is so fragile that it's impossible to mount it on the micro scanning platform. Now, if this path is chosen, the scanner will not swing the platform, but will only rotate it. Now, on this slide, you can see the main accessories that you need to use when working with the micro scanner. At the top right, we have the calibration board, which is used to calibrate the scanner. The calibration procedure takes only a couple of minutes and is fully automatic. It must be done upon first launch and is highly recommended to be repeated each time after the scanner has been moved or transported. Then on the left, we have an entire tower of components which can be interchanged, added, or removed depending on the type of object being scanned. Number one, the vise, is used to hold very small objects. It magnetizes to number two, the gum jig. Number two can also be used without the vise by sticking the scanning object to it with blue tack. That's the sticky chewing gum-like stuff that you see at the far bottom right. Number three, the screw jig, can either be used to hold number two, or it can be used to screw in a large object directly, sort of like a large vise. Then there are two spacers. They are both marked as number 4. Both of them are magnetic, and they are used to regulate the height of the setup. It is possible to scan using 0 spacers, 1 spacer, or both spacers. Now, if you're scanning a small object and high resolution is important, both spacers should be used in order to have the object as close as possible to the camera. When scanning a mid-sized object, it is possible to use 1 spacer. And for a very large or tall object, it may be necessary to remove both spacers. Now, this last scenario with 0 spacers was, in my experience, very rare. Here is a visual example of variable spacer usage. On the left, the ball was sitting on 0 spacers. It was too far away from the camera and was not really scanned properly. The resolution would, in this case, also be less than desirable. Then in the middle, the ball was sitting on 1 spacer. The result is much better, and the ball could be scanned in this way. 1 spacer appears to be an adequate solution for this ball's size. Then, sitting atop both spacers, that's on the far right, the ball was also scanned well, at least in terms of surface quality. We do notice that there is less coverage, with only one side of the ball having been scanned. This means that for a ball of this size, we would need to reposition it multiple times in order to get a full scan. While this may be inconvenient, it could be worth it if the resolution is crucial. This is because being situated closer to the camera will give us a higher resolution overall, potentially capturing minor scratches and surface defects on the ball. And then, speaking of resolution, in Artec Studio, we have a high resolution checkbox. If enabled, the dataset will be much larger and denser, but it will allow you to capture much finer geometry. As you can see on the image to the far right, the high resolution mode captured tiny surface scratches that were not visible when scanning in normal mode. Then on this slide, you can see a variety of methods that can be used to mount an object on the scanning platform. There's the option of using the small screw vise for small objects, the large screw jig for much larger objects, and the gum jig, which is the black flap platform, for sticking on objects with blue tack. Also interesting and worth mentioning, the blue tack balls that you see around the rat on the picture at the top right have nothing to do with holding the rat in place. Rather, they're being used as registration aids for the global registration algorithm. For those of you familiar with the space spider, you probably know that a texture background can greatly assist the global registration algorithm when you're using the geometry plus texture registration method. Now, due to the Artec Micro's high precision, the global registration for microscans can only be launched in geometry-only mode. Therefore, any registration aids for the micro need to be geometrical. This is similar how you would help yourself when using an EVA light scanner, as you can see here on the red card. Now for the micro, the easiest and fastest form of added registration geometry is to use random balls of blue tack, like the ones that you see placed around the rat. It is worth mentioning that this workflow only makes sense for very small objects or for objects with poor geometry. Large and geometrically rich objects will be registered correctly without any assistive geometry, because their own geometry will be more than enough for the global registration algorithm to work with. So now that we've covered the basics, we can start on the workflow. On this slide, you see a couple of objects being scanned. Now, regardless of the mounting method and the registration aids being used, the scanning process is fairly identical and takes around 2 to 5 minutes per side. After that, the object can be flipped over and the other side can be scanned, taking another 2 to 5 minutes. But let's talk specifics. The basic scanning workflow is roughly as follows. Number 1, first you need to mount the object on the scanning platform using one of the methods mentioned previously. Number 2, it's very important to adjust the camera brightness setting. You want to brighten up the object while avoiding overexposure. Artec Studio offers good visual feedback for this, so any overexposure will be highlighted in red in the preview window. Number 3, select the automatic scanning path and launch the scan. You may also want to enable the high resolution mode and color capture if you need any of those. The micro will pan and rotate the object on the platform and will perform an initial scanning run. Then, based on the first set of frames that it collected, it will plan its path accordingly and will continue scanning in order to cover any areas of the object that still remain uncaptured. Number 4, after the object has been scanned completely, as per the algorithm's judgment, you may flip or reposition it on the platform and launch a new scan. If the auto-align new scans with those marked in the workspace checkbox was ticked, the new scan will be aligned with the previous ones on the fly while the scanning process is still going. And in number 5, you can see a nice example of the automatic alignment. 2 scans of an electronics board, an Apple iPhone charger to be specific, have been aligned successfully. This auto-align feature is compatible with medium to large objects. Keep in mind that it will not always work on small objects, nor will it work on objects with assistive geometry on the platform, like the rat on the right. In these cases, disable the auto-align and perform a manual alignment after scanning. Reflective objects present an additional yet well-known challenge. Their surfaces chaotically reflect the scanner's projected pattern, making the object practically invisible. So, as with other light-based scanners, the solution is to simply cover the object with a temporary coat of non-reflective spray. The key difference specific to the micro, though, is that not all types of spray will suffice. With its super high resolution, the micro scanner is able to capture the flakes or grains of most standard out-of-the-can scanning sprays. And in addition, these standard thick particle sprays can also mask fine surface geometry on the object. So for these reasons, we highly recommend getting an airbrush system to use in conjunction with your microscanner. I mean, the additional cost is minor, while the benefits are certainly worth it. It's also worth noting that because the projected pattern is blue, some very specific shades of red may not be scanned well unless they have been sprayed beforehand. Here on the right on this slide, you can see a picture of the airbrush system that we use in-house. It is a top air compressor with an Iwata airbrush. And the scanning sprays available for these airbrush systems, they come in the two usual types. There's the magically disappearing and the wipe-off variety. And here in the bottom right, we have some examples of the brand of spray that we, once again, use in-house. When scanning very small objects, the proper preparation and approach are key for achieving great results. For best accuracy and resolution, the object needs to be positioned close to the sensor. So make sure that all the spacers are in place, with the object firmly mounted on top of the structure. Note that the object should be mounted very well in order to avoid any shaking or shifting on a platform. Next, creating additional geometry on the scanning platform is another key element for success. So as mentioned previously, something as simple as randomly positioned blue tack blobs surrounding the object will later help the global registration a great deal. Once the scanning is done, global registration should be performed with a keyframe ratio of 1 for each scan individually. Then, use the lock feature to freeze the frames in place after all the individual per scan registrations have been done. So, after you've globally registered all the scans individually and you've locked them, the next step is to clean up the extra geometry and support structure using the eraser tool. Then, align all the scans together and do a global registration. Because the scans are all locked, this global registration will perform a sort of fine align on your locked scans. After that, you finish up with the usual steps of fusion, mesh simplification, and texture mapping as needed. Moving from one extreme to the other, let's briefly discuss large object scanning. In terms of registration, this is actually much easier than with small objects, as the object itself will usually have sufficient surface features for a successful registration. The most important recommendations for scanning large objects are as follows. So first of all, you need to remove one, or if necessary, both spacers, allowing the object to fit into the field of view of the scanner. Second, use a powerful PC with significantly more RAM for processing, since larger objects will result in much heavier and more performance-demanding datasets. And lastly, if the object is so large that it doesn't really fit into the scanner's field of view, or if it is simply too large to be safely rotated inside the scanner, in this case, scan it using the single frame capture mode while manually repositioning the object on the platform between your shots. Now that we have gone through the workflow from beginning to end, let's introduce some visual examples. Here you can see the octopus ring that was shown earlier in the presentation. It was captured using 3 scans, so 3 different positions, using the automatic scanning path for each position. And here we see how the ring was post-processed. So we start by cleaning up all 3 scans with the eraser tool. And you see that happening in the video right now. So I'm selecting the scans one by one and getting rid of the supporting structure. The next main step, we align all the scans together using the Align tool. a couple more small eraser touches. And next, the global registration is done. Then comes the fusion, which is the step where all the raw data frames are turned into a single mesh. And that's what is happening right now. So after the fusion, we apply the small object filter, which removes any fragments that may have been reconstructed in midair. And last but not least, the polygon count of the model is optimized by using the fast mesh simplification algorithm. And that's it. I would call this the simple workflow, and it is mostly applicable to medium-sized and large objects. This fake gemstone, which is actually made out of glass, was captured in 2 scans. An initial third scan was unsuccessful because I had not airbrushed the surface enough and the gem was still partially reflective. Now, this problem was solved by applying a little bit more spray, obviously. Then while scanning the gemstone, I accidentally dropped it on the floor and a piece of glass broke off. But I decided to glue it back in place and to continue scanning just to see how visible that crack would be in the final scan. And on the resulting model, we can clearly see the crack and some small bits of glue residue around it. Now, thanks to the scanning spray, the overall surface of the gem was indeed scanned very, very well. And because the micro has such a high resolution, it's important to keep the object very clean while scanning, because any dust sticking to the surface will be captured and then will be visible on the final model. Actually, on the gem, if you look closely, you can find a couple of dust specks on the surface. On this slide, we see the results of scanning a small California-shaped pin. Now, despite the pin being shiny, we managed to capture it in color. This is due to a special workflow detailed as follows. 2 scans, so 1 of each side of the pin, were done in color and without spray. And then 2 more scans were done in geometry-only mode after the pin had been sprayed with the airbrush. The scans were then processed separately in matching pairs. The airbrushed scans were used for the fusion to create the geometrical model, and the non-airbrushed scans were used to map color onto this model. This is a workflow that can be used for most types of reflective objects where color capture is also needed. Here we see a time lapse of how the pin was post-processed. So first of all, 4 scans were cleaned up with the eraser tool. Now remember that 2 of the scans are geometry only, while the other 2 contain color information. So we're still cleaning up the scans. You see that happening now. Okay, next step, all the scans were aligned using the Align tool. So after that, a global registration was done for the geometry-only scans. Then a fusion was made from the geometry-only scans. Following this, the texture from the 2 scans containing color information was applied to our fused model. Finally, some small adjustments, and you can see the result. That's it. Here, we see the model resulting from scanning the internal electronics of an Apple iPhone charger. This was scanned and processed using the same method as for the California pin. So first, 2 scans were made in color and without spray. And then the other scans were made with spray and scanned using the geometry-only mode. So everything exactly the same as you saw in the workflow for the California pin on the previous slide. Okay, here you can see the result of scanning an iPhone SIM tray. This tray was processed using the small object workflow with assistive geometry on the base. The resolution of the model is actually detailed enough to see some small dents in the soft aluminum material, as well as make out some scratches around the ejector hole. I have marked those with red circles in the photos on the left. And then if you look closely in the video, you'll see me point out those defects with the mouse. So here's one, and then here, and then here are those scratches around the ejector hole. Now here's the workflow that we used to post-process the SIM tray. It is very clearly the small object workflow. So we start by performing an individual global registration for each scan with the assistive base geometry still present. Next, all the bases are erased. That's what you see happening right now. There we go. Then we align all of our scans. Following this, we lock all of our scans, a very important step in the small object workflow. And after that, we obviously perform another global registration, which finalizes all the scans together. Finally, we do the fusion, and we get a model. You'll see me clean up the fusion, removing a blob that has appeared in midair, probably due to some piece that I neglected to erase earlier. But apart from that, that's it. Here, we have a nice example of a fairly large object. So the measurement numbers are shown in millimeters. This object fit into the screw jig, but barely, and was scanned using only one spacer. And here are some other objects that were scanned with the micro, including a small heart pendant, a Libra pendant, another small jewelry item, as well as a screw. Here you see a small fossil. It's around 10 millimeters in diameter, and it was scanned in color. This scan is of a small bird skull. The beak is around 8 millimeters long, well, depending on where you measure it, and it has tiny 2 millimeter breathing holes in it. On this slide, we have a hole that is around 1 millimeter in diameter. And here we have a protrusion that is 0.6 millimeters in diameter. Then here's a scan of a tiny figurine that is just less than 2 millimeters wide. That central bump inside the hole is a mere 0.38 millimeters wide. And here we have a height change of 0.3 millimeters on the surface of the scanned object. This was measured using the Construct Primitives functionality in Artec Studio 15 by using two planes that you can vaguely make out here. As you probably noticed throughout this presentation, the Artec Micro has a vast number of possible applications. So it can be used for quality control, inspection, reverse engineering, heritage preservation, and so much more. All right. That's all the material that we have for today. I think Elena now has something to show us.
Thank you, Vadim. And before we move on to the Q&A session, let's finally check out what Dima got. And here is the final model. So the entire process took about 20 minutes, and scanning and processing actually went smoothly because Dima followed all these recommended practices that Vadim mentioned in his webinar. And thank you, Dima, very much. And thank you everyone for attending our webinar today, and make sure you subscribe to our YouTube channel so you don't miss any new videos.